let's start then today's class. So yes, it is recorded. Okay, so what we have done, so far we have learned what is chaos, and we have seen that logistic map which actually map the discrete population growth contains means its dynamics. While it looks very simple maps, which is xn plus 1 equal to r xn into 1 minus xn, so this is very simple looking dynamical map. However, the dynamics, or the as we evolve the time, or whenever we iterate this simple looking map, we will find a very complicated kind of dynamics which is characterized by, which is actually known as chaos. Why it is chaos? Because although it is deterministic, we cannot predict its future. So that we have seen, and we, as well as numerically as well as theoretically, and theoretically for only parameter mu equal to 4, we have proved that this logistic map, or any kind of one hump compact map which remains between, which maps the interval 0 to 1 into interval 0 to 1, every such maps is can be, means every such map will generate chaos. That we have proved, that we have proved. Now from today's class, I will be discussing the new concept which is called fractals. So let's start doing fractals. So let me start. So from today we are going to learn these fractals. Okay, so why we are interested in fractals, why we have suddenly jumped from this chaos to fractals? So this is the first question that will come to our mind, why we suddenly jump from chaos to fractals. Now if we recall, when we numerically uh, proved that the logistic equation has chaos in itself, what we have done, we have shown that orbit diagram we draw orbit diagram through the help of a computer, and we have seen that at every, and if whenever we change the parameter r, a period doubling bifurcation occurs, and this period doubling bifurcation occurs at it's not only one time. Whenever we change or increase this parameter, and next period doubling bifurcation of previously every branch of the period doubling period double orbit again bifurcate, and this bifurcation does not stop in any finite value. It actually bifurcate infinite times. So when it bifurcate infinite times, not only that, every this bifurcation diagram, or twig like structure, it is tree branch like structure or twig like structure, bifurcate again, and all the bifurcation twig looks similar, and they are self similar. So that's why its structure will be quite complicated, and if we want to characterize what kind of structure it is, we have to know the chaos. So let me show you the bifurcation diagrams once again, then it will be clearer. Yes, here you see whatever I am saying in words. So you see the first bifurcation occurs at r equal to 1, but whenever I change or I increase the r a little bit, another bifurcation occurs at less than value of 1.5 or some value at, and then if I increase these, suddenly these two branches again bifurcate, and this pattern continues. And not only that, we also seen in the class that these near this bifurcation point, this twig looks exactly same at every bifurcation point. So the whatever twigs looks like here, the same, if I increase or renormalize this part of this twig, it will look like same as the previous one. And this also, this if you see the smaller structure, so let me increase this much. So this smaller structure, if I increase this smaller structure, this will be also look like same. Okay, let me see one thing. So if I only increase this part, you will find this actually looks same as the previous one, only a smaller version of that previous one, and I zoomed out, that's why it looks same. So that means this orbit diagram or chaos itself contains continuous self-similar structure into itself. So whenever we whenever we zoom out any smaller part of this bifurcation diagram, you will find that you will find that every smaller region looks like the same. So this is a quite complicated structure, and this structure, from this structure anyone could say that this is looks like that it is a it is it is not one dimensional, because whenever we will see through this in this class, you will see that this is actually not one dimensional structure. This is called fractals, and we will define what is the dimension of these fractals, and how can we characterize by mathematics this structure. So this is our motivation. That's why we have jumped from chaos to fractals, because in chaos itself the fractals appears. And if I want to know what kind of structure it is, we have to know a little bit of mathematical background of the fractals. So that's why. And not only that, in nature we actually always seen everywhere this fractal kind of structure. So as for example, like a mountain range. So whenever see you mountain range, and if you zoom out in any mountain, you will find that zoom out a smaller, same like a smaller kind of mountains, the same shape will be there but in the smaller range. So what I mean, so if you see a mountain range, so mountain range from outside look, you will see a larger cone like shape. But whenever you zoom into these mountains, you will find that inside that mountains there are again smaller that mountain like shape, only its size reduced by some factor. So a mountain range is not like a exactly like a cone like shape, but it contains many complex cone like structure. So it, you can't characterize the exact structure of this any mountain range by any cone. Similarly, the structure of the clouds is also quite complicated. You can't characterize the shape of the clouds by any kind of known geometrical shapes like sphere or square. And even if you found it, since this is winter and you will found in your home this broccoli, and this broccoli also has some complicated shape, and this broccoli can also be, the shape of the broccoli can also be characterized by these fractals. So because of these complex beautiful looking things, for the graphics design of the computer, it has a large application. And we are not going deeper into the application of the fractals, and also we are not going deeper into the mathematical beauty of the fractals. But what we will do, we will introduce the subject, so as we can find out something about the orbit diagram that we have seen in the study of chaos. So that is our motivation. So That's why we need to know the fractals. And since fractal is a mathematical concept, and since infinite fractals means in every smaller regions it contains a self similar copy of itself, so it means fractals contain infinite elements which look same similar to whole structure, or means it is as complicated as the whole fractals. So that's why it is we have to know some concept of the set theory, which is infinite set. So let me edit infinite set. To study the fractals we need to know some characterization of infinite set. Okay, now uh, there are two types of characterization of infinite set. One is called the countable, one is uncountable. So due to the mathematician cantor, this is mathematician due to mathematician cantor, actually we can characterize the sets. So let's first see one thing. So first one to one, let's see one to one correspondence. So suppose x is a set and y is a set. So if I find a y, suppose if I find a y which belongs to y, and for every y there exists a x which belongs to x. So that means for every element of x we will find every element of y. So that is called the one to one correspondence. So we can say like that, so we can say like that that for there is this is called the body system. So for every element of x there is a body who's sitting at y. So this is called the y has a one to one correspondence. And if we can find this one to one of correspondence, we can say that okay, we can say that x and y have same cardinality. X and y has same cardinality, same cardinality. And it basically says that the element number of element contents in x and number of element contents in y are same. So this is thing. Now here is a one very interesting and bewildering concept exists there, that that some infinities are larger than some infinities. So at first it seems very confusing, but let me give an example, then it will be clearer. Suppose actually now let me define first the countable and uncountable sets. Uncountable sets, suppose any set x will be called countable. So countable if we find one to one correspondence of this set with this natural number set, which is 1 2 3 4. So if we can, that means if we can actually count the number of elements in the x, like the first element is 1, second element is 2, third element is 3 4 5, then we call is countable set. Now if and if a set is not countable, then we say it's uncountable set. So let me give you an example. So and it is, suppose so that let me give an example, so that the set of number e 2 4 6 is countable. What does it mean? It means that the cardinality of this even number of set and the this natural number 1 2 3 4 is same, and you find it very means at first I find it very confusing, because you see that this even number of set does not contains any odd number. So from the natural number, if I move all the odd numbers, then only remaining one will be called the even number set. So since I am taking half of the number out of this natural number set, only half of them should be there, but it is not the case. If you can see that since that every number can be corresponding to this natural number set, because 2 can be written as 2 into 1, 4 can be written as 2 into 2, these can be written as 2 into 3. So in general, any nth element can be written in terms of 2 into n. So that means we can count these numbers by these 1 2 3 4 5 6 n. The n element can be represented by this n element of this natural number. So that's why we can say that E is countable, because we can count them, or E has a one to one correspondence between E and this natural number set, and these two have same cardinality, and this is why it is countable. So that's it. Now another, let me give you an example. Another, so it should not be that we actually write it 1 2 3 4 5 6 in this term, but in any manner if we can count them systematically, we say that say it is countable. So let me give another example. So so that so that the positive rational number are countable. So we will do that. So in our first if we want to try it, so whatever we will try first, we know that what does this rational number means. So any numbers that can be represented by this p by q form, we will call this a rational number. So we want to prove in this way. So first of all we will write 1 1, then we will write 1 2 1 3 1 4, and we will find this. But one problem is that, because if we start to writing in this way, we will not find this number, that is 2 by 3, because if you write in this manner, you will find that you will never, since it contains infinite numbers, it will, this sequence will never ending, and you will you cannot start a number like 2 by 1 2 by 2 and this kind of thing. So that's why this is not the way one should prove this. So the proof is that you will write a matrix whose pth p means whose at the, so if I write a matrix, suppose, and p by q, pqth entry is p by q, means if I go from this column, means, okay, let me write it. So first column, for the first column every p value will be 1, so 1, and q will be changed, because this q will be the, so p is the row, no, and q is the column, no. So that how you will find this p by qth element. Now first will be 1 by 1, then 1 by 2, then 1 by 3, then 1 by 4, and this is the thing. Now then in the second row it will be 2 by 1, 2 by 2, 2 by 3, 2 by 4. The third similarly 3 by 1, 3 by 2, 3 by 3, 3 by 4. In the fourth 4 by 1, 4 by 2, 4 by 3, 4 by 4. Now how you will find any number? Suppose I want to find this number. So you will see that how how I will go through these. So first I will go from here to here, then I will come back diagonally, then again I want to go through the diagonal. So every time I came to a point, then I want to go from diagonally. That's how I will progress this set. So first it contains 1 by 1, then 1 by 2, then 2 by 1, then 3 by 1, then 2 by 2, then 1 by 3. Then again there is no way to go towards diagonal, so that's why we shift 1. Now we will again find a diagonal. So again we will find, go here and go here. So that way this set content. So now since we cannot go diagonally, so that's why we will go below here, and you will find somewhere some number here, and from here to you will go here, go here, go there, and so that's why that's wavy manner you will. So first here, then here, then here, then here. So then in this wavy manner you will systematically go to any rational number in a finite state. So here to come to this rational number, how many step I required? 1, 2, 3, 4, 5, 6, 7, 8. So after 8 step you actually come to this element. So that's it. So that's where you can go. If we actually arrange the rational set of the rational number in this manner, you will eventually in a finite step you will find any rational number. That's why the set of the rational number is countable. Now let me give an example of this uncountable set. Let x denote the set of all real numbers. All real numbers between 0 and 1 so that x is uncountable. Now let us show. So we will prove this by contradiction. So first of all, let us assume that we in principle means let us assume that this set of real number is actually countable. So we can count this set, the real numbers, all real numbers between 0 to 1 by a set which can be represented as this. Suppose x1. So x1 is a one real number, then the next real number is x2, then the next real number is x3, and so forth, so on. So similar to here. So first irrational number is 1 by 1, 1, then 1 by 2, then 2 by 1, then 3 by 1, then 2 by 2, then 1 by 3, then 1 by 4. So this is x1, this is x2, this is x3, this is x4, this is x5, this is x6, x7, x8, x9. So that's why, that's the way, actually let assume that we can write this any number between any real number between 0 to 1. So, and if we can write that, then we actually say that this is a countable set. So there is no problem. So let us rewrite this x1 in the decimal sense. 0. Suppose x11, x12, x13, x14, x2 is 0. So in this way, that x21, x23, x22, actually x22, x23, x24, x3 will be 0. x31, x32, x33, x34. So in this way you actually write every element where this xij is the jth decimal of the ith real number. So if it is complete, that we cannot find any number between 0 to 1 which does not contain in this set. So if I can find a number, suppose r, which does not belong to this set, then we actually prove that. So this is actually not a complete description of between complete set which contains all the points between 0 to 1, because we can write a number that actually is not there. So let us construct this is called the diagonal argument. This is also discovered by this is also used by this contour. So what we will do, so basically this x11 is a digit between 0 to 1, 0 to 9. So let us construct a number r by this. So in the first digit, what I will write, so I will write any digit not equal to x11. So suppose we will write x11 bar, which is x11 bar not equal to x11. It can be anything, only it can't be equal to x11. Then in the second digit we will write x22 bar. So that means it can be anything, but it can't be x22. In the similar way, x33 bar, in the third digit I will write this the element which is not equal to x33, and so far so on, and the is nth digit we will write it xnn bar. Now you see that this r does not contain, this r actually is not there, exist in this set. Why? Because this r can't be x1, because the first digit is different. The r can't be this second number, because the second digit is different. R can't be third, because this third digit is different. Because x33 can be anything but not x3, so third number is, so xn, it can't be xn, because this nth number is different, and it can't be anything in this. You can't you cannot find this r in this set because of this reason. So whenever you will find any n, if you want to see that whether or not this n, this is r is corresponding to any n, you will find that there is no n for which this r is actually the xn is equal to r. So you will find there is no n for that xn equal to r. That's why that this r actually does not there in this set. So that's why it is said that you will actually always find a number which does not contain in this set. That's why you cannot write a set, um, means you cannot write a systematic complete countably set. That's why it is uncountable. You can't count actually, or you can't systematically write in this way x1 x2 x3 these numbers, the number, all the real number between 0 to 1. That's why it is uncountable. So this is the example of uncountable set. So let us uh, now let us go astray from this. Now let's going to, since we know what does this countable set means, what does uncountable set means, now let us give an pedagogical example of the fractals, which is called the cantor set. Cantor set. So let us show this cantor set. So suppose you draw a line 1 to 0, so 0 to 1. So that means uh, all the point is there between 0 to 1. So let me, so this S0 is a set which contains all the points between 0 to 1. Okay. Now suppose this is 0. Okay, this is 1. Now suppose that you take this part, middle third of this, suppose that you from this S0 you take away from this middle part, so 0 to 1 third, then this 1 third, this is 2 third to 1. Now S1 contains all the points, but it doesn't contain this part of these points, so 1 third to 2 third point it doesn't contain in S1. That's why you build from S0 to S1. Now you apply the same pattern to make, let me do it. Oh, now again you repeat the same thing with these also. Suppose okay, no, okay, let me bring here that I have generated from the computer, so that will be much more convenient. Let me bring that one. So yeah, this is it. Okay, yeah, it is much more convenient. Okay. So this is the cantor example of the cantor set that I want to draw here. So this is first S0. Now from S0, if you take the middle one third part, take away, then you will what is left with, this is called the S1 set. So S1 set contains all the point from here to one third, and then two third to 1. Then you repeat the same thing. So that means you take these things and just take away this middle third part, and the remaining one you just left that remaining two, and same thing you will do here, and this way you will find S2. And again if you repeat this thing, you will get S3, and if you repeat this thing again, you will get S4, and this way, and this is S5. Now, so if you repeat these things infinite times, then what structure you will get, that is called the set contour set, that is S equal to C equal to S infinity. So that is actually called the contour set. Contour set. So how you construct in this way? So you take the all the points between 0 to 1, then you just take mid one third part, then again you repeat you will, that's way you will make S0 to S1, and from S1, that whatever left with, you take the middle part of the every part, that you just take the left part and take the middle part away, that's way you will get these things, and again the same thing will happen here, that's why S2, and from S2, every from every part you will take the middle third part, you will get these things. So that's the way to uh, get this infinite complex looking structure, that is S in C equal to S infinity. So at first it actually to think about this S infinity, it is quite complicated, but you can think that S4 S5, that is that's the way you will see. Now let's write here some property, which is the property of this contour set, which is actually the property of the fractals. So let me write the properties. Fractal properties of the contour set. Fractal property of the contour set. Okay. So let first property 1 is this C has structure at at arbitrary small scales. If we enlarge part C repeatedly, actually what I am saying, that C has a structure at arbitrary small scale. So it's just think about that this structure. So you find that uh, when these become S infinity, you will find that there are infinitely complicated looking shape is there. So what is the shape? So every time you will find that there are points appearing, but the gaps between them are different size. They are not quite arbitrary shape, but you will find that one third gap is away between 2 points. Any 2 points you will find, then any the points are separated by different kinds of different separated by different various sizes. So that is the shape. in whichever smaller scale you go, which means if you zooming out, or if you in the smaller scale, if you go smaller scale in the set C, you will find that the same structure is appearing, same complicated structure is appearing as it was in between 0 to 1, that there are points which are different, or they are separated by various sizes of the gaps. So that kind of complex structure is there. So that is the basic of the fractal. So at every scale you will find some kind of complex structure is appearing. So it is like that, a world within world which is never ending. So you will find that a world. So let me give you a very good example. So here you will find that. So this is the thing I am wanting to say, that within in the screen you will first find a window, then inside this window there is a smaller window, then inside that window there is another smaller window, then there is another smaller window. So these structure actually repeated infinitely. This is the property of the fractal. That property is also there. Whatever small region you will go, uh, this this structure will repeat itself. So it's like that, a world of window contains a window, and that window again contain again one window, then every smaller window contain that window. So that's why it is called the fractal. So these properties also there in the fractals, this cantor set. So that I'm talking about. Then the second property is C is self similar. C is self similar. So it means it contains smaller copies of itself at all scales. So that means if you take only left part of C, and if you increase its size, the left part of the C, if you increase its size by 3 times, you will find that you will find that you will again find this C. Means in C, if we good means if you increase the size 3, we will get back C. Now if you take the left of the left part, or any part left of the left part, or the right part of this left part of the C, and if you multiply it, means if you increase by its 9 times, you will again get back C. That means the every smaller copies of C actually contains C itself. So this is a self similar properties, but it is actually quite bewildering to thought. So that's why let's see about this way. So from here you see, from the contour set, so if I take this part, and so since it's 0 to 1/3, now if I increase it 3 times, I will get back this S1, because 0 becomes 0, 1/3 becomes 1. So if I increase this, I will get S0. Now similar to this S2, if I take this part and increase 3 times, I will get S1, because this is 0 to 1 by 9, and this is actually 2 by 9 to 1/3. So that means if I multiply this 3 times, I will get back this S1. Similarly from here to this whole structure, from here to here. So that means if I take S n's left part of Sn, and or Sn plus 1, and it increase 3 times, what I will get? I will get whole Sn. So left part of s plus 1. If I increase it 3 times, I will get whole Sn. Now if I go to this infinitely, then what it will say that this left of s infinity, if I increase it 3 times, I will get whole s infinity from here. So that means left part of C actually contains C. If I left part of C takes the left part of C, I will increase 3 times, what I will get? I will get whole C. So that means the C actually contains the C itself. Now since this left part of C contains whole itself C, I include 3 times, so if I takes the left part or any part of the C and multiply it is 3 times, I will get whole left part. And if I, that means from here left of or middle or left of left part, right click this left of left part of this left part of C. Now if I multiply 9, I will get the whole C. So this is the called the self similar structure, but there is a warning. This is only true for this cantor set, so that's self similarity. So this is exact self similarity, but the fractal does not have this exact self similarity, always does not have this exact self similarity. It could be like this way also, that statistical, the strict self similarity of cantor set is found only in the simplest fractals. More general fractals are statistically self similar. Now third is, this is the property, third property is the dimension of the C. So first of all, since what is the dimension of the C? So you see, this is not actually quite a straight line, so quite not one dimensional, it is less than one dimensional. So you will find, means in the later classes we will show this, that the dimension of the C is actually not an integer, rather it is a number, that is ln 2 by ln 3. The dimension of this C is ln 2 by ln 3, cantor set, that is actually 0.63. So this is also a property of the fractals, that its dimension is not integer. That's why we can't represent, or we can't associate some familiar geometrical object with these fractals, because that familiar geometrical objects have the integer dimension, but this fractal has the fractal dimension, so that's why it is called the fractal. This is fractal dimension. So that's all. Now this cantor set has another two property which is not related to fractals, which are actually one, is that the length or the measure, the cantor set has the measure 0, and 2, that cantor set contains uncountably many points. So at first it seems like that, since we actually take 1/3 part away from the line every time, so it contains, actually at the infinity it contains no point, but it is not the case. It actually contains uncountably many points. That means it contains many numbers, means it can actually large number, means it's actually contains very large number of points, actually that is actually, if you say, if you compare it with this set natural number, you will find that this counter set contains more number than natural number. So that's it. Now that's why we can't represent this contour set, or we can't find a one-to-one correspondence between this contour set and this natural number. So that's it. Now this proof is very simple. First proof is very simple. So because you see why it's measure 0, so here if I go back here, if I go back here, you find that at x0 what is the length, if I measure it, what is the length of this is 1. Now if I go to s1, what is the length, it is 1/3, and this is the length of 1/3. So this s1 length is, length of s1 is 2/3, this is 1, this is 2/3. Then length of s2 is, this is 19, this is 19, this is again 19, this is again 19. So this is 4/9, actually 2/3 square. So you find that at s3 length of s3 will be 2/3 cube. So that means the length of the measure, so length of Sn actually will be 2/3 to the power n, and c is actually n tends to infinity. So length of c means limit n tends to infinity Sn, length of Sn, so that is 2/3 n limit n tends to infinity. Since it's a 2/3 is less than 1, so whenever we multiply 2/3 itself, it will decrease. So as at infinity 0, it goes to 0. So that's why the length of c is actually 0. And if we actually since this is contains the three parts, so we represent this contour set by the decimal, means in this way. If we represent in the basis of 3, we find that this is uncountable, and the proof is in the similar line as we have proved that the numbers between 0 to 1 is uncountable, real numbers 0 to 1. So before that you have to represent this number, any number x is like this way, that a1 by, in the basis of 3. So first a1, which dictates that point is in the range of 1, it is in the range of 1 to 3, or it is in the range of more than that, plus a1 by a2 by 3 square plus a3 by 3 cube. So that's why you have to represent. So let me, I will not prove that, but let me sketch the proof here. So any point, so the any point x can be written as 0 point a1 a2 a3, this way. Now let me first go here. You see from here to here this is less than 1/3, so that means here the first a1 is 0. If a1 is 0, if a1 is 0, we know that it actually, the value, if a1 is 0, its value is less than 1/3. The x1 value is less than 1/3. Since from here to here this is less than 1/3, so that's why 0.0, and here it is greater than 2/3, so that means it is actually greater than 2/3, so that's why we will put here 2. So if a1 is 2, so that means it is greater than 2/3, and this middle part actually is 0.1. So that says that it's actually greater than 1/3 but less than 2/3. And here again also, since if we consider this part, this actually is 0.00, so this part is greater than, it is less than 1/9, so that's why you go here. So this is 0, this is a2 means 1/9, So if it is less than 1 by 9, then this part A2 should be 0, and this you will find that this is 0.01 because this is greater than 1.9, or it is not greater than 1.9, it is actually greater than this is 1 by 9, this is actually 1 by 9, this is actually 2 by 9, so it should be 2. Similarly here also this is 2.0, this is will be 2.1, and this is actually 2.2. so that's way you will find you actually you actually represent any number, any point which any element which belongs to the set C in the base of 3, and whenever you can represent the number in the base of 3, then from the same reasoning what we have applied here, so you can then always assume that you can actually you can write the number of elements whatever is there in the C in this form x1 x2 x3. only difference is it is in the form of decimal, but now you write it in the form of basis of 3, and from the using the same logic you will prove that you will always find a R which is actually not belongs to this set. So that's why there is no possible set by which you can systematically write the all numbers. So that's why it cannot be counted as 1 2 3. That's why it's uncountable. So that is the general proof. So that's it. Now in the next class I will we will discuss about this dimension of these fractals. Those there are in general 3 dimension. One is called the similarity dimension, one is box dimension, and another is point wise and correlation dimension. So in the next class we will find out this concept of the dimension. So that's it. So thank you.